All right, so in this section we want to learn how to name our binary molecular compounds. So our formulas for so binary means two. We've only got two atoms that are going to be involved in the molecular compounds that you'll be required to name. Once they start getting larger than that, the nomenclature becomes a little bit more complex, and you'll learn more about that in Chemistry 105 if you continue on with this and we start talking about organic molecules. So right now you're only required to be able to name binary molecular compounds, or molecular compounds, covalent compounds that contain two atoms. So our formulas of binary molecular compounds are written then with the less electronegative element first. The more electronegative element comes second in our compound structure. So you can kind of equate this to what we saw with our ionic bonding, in that the cation or positive thing comes first and the negative thing comes next. It's the same with our binary molecular compounds as well. The less electronegative or more towards the positive side is going to come first. The more electronegative or the more towards the negative side is going to come second. So the first one, we're going to name the first element in the formula using a prefix to indicate the number of atoms. So with ionic compounds, we needed to indicate charge states when we were naming the molecules. With our molecular compounds, we actually need to indicate the number of atoms that are going to be present within the molecular formula, since we don't have charges to go by. And then the name of the second element, we still use the "ide" ending, and we also have to have a prefix if it's needed for multiple atoms of that element. So let's look at some examples. So first of all, we have to recognize covalent compounds and tell them apart from the ionic compounds for our naming. This is easy to do. So how do we do it? We remember that covalent compounds are made up when nonmetals are mixing with other nonmetals. So it's going to be ionic if we have a metal and a nonmetal coming together. So that's our first division. We have to say, is our compound ionic or is our compound covalent? And then we can go on with the naming. So if we have a water molecule, for example, we know that this guy is going to be nonmetal plus nonmetal. This is going to be a covalent bond. Carbon and oxygen are going to be the same way. We've got nonmetal and nonmetal coming together. This is going to be covalent. How about ammonia and hydrogen? Yes, both of these are nonmetals, nonmetal and nonmetal coming together, covalent. This one is not a binary compound anymore, but it is still a covalent molecule. It now has 3 atoms. So it's a tertiary molecular compound, if you wanted to say that. It's got carbon, hydrogen, and oxygen in it. All of these guys are nonmetals. So this is going to form covalent bond again. So some of these have common names. They're memorized, but they are common, so they're not too bad. The ones that you'll need to know are water, ammonia. We see this a lot, so you need to know NH3 is ammonia. And bicarbonate is also very common, or baking soda, but you don't need to memorize this one. You should know ammonia and you should know water. And this one is actually a combination of ionic and covalent. So this is an ionic compound, but you can see it's polyatomic, right? It's got a polyatomic anion, and it's got the metal as the cation in this case. So this is an ionic compound, but the bicarbonate part down here, so we'd say this is sodium bicarbonate, and I told you didn't have to memorize the polyatomics. They're given to you in that table. But the bicarbonate portion of this molecule is covalently linked together. The hydrogen, the carbon, and the oxygen are all nonmetals, and when they come together, they're sharing electrons. That's why our polyatomic ions will move together as an anion unit, because they're all committed to each other, sharing those electrons. They cannot disassociate when they go into solution. The sodium, because it's ionic in nature and it's donated the electron to the bicarbonate portion, is going to be able to dissociate into the solution when you dissolve baking soda into water. So when we're doing our naming for our binary covalent compounds, binary again means two, so we've got two atoms. So binary covalent molecule refers to molecules with two types of elements sharing electrons with one another. So these would all be examples of binary molecules, and you should be able to name these by the time we get done with this section. So naming for these guys is very easy if you know your counting prefixes. So these guys are the counting prefixes that you'll need to know. Mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa for 8, nona for 9, and deca for 10. So you're going to need to memorize these prefixes going with this number of atoms involved in the bonds. So our rule, we have a prefix plus the least electronegative element, another prefix plus the most electronegative element modified with the "ide" ending that we saw with our ionic compounds as well. So at the beginning of the molecule, if there is only one atom of the element, you do not need to use the mono prefix at the beginning element. However, if the ending element only has a single atom represented, you do need the mono prefix with the ending element. So if we have a molecule of N2O3, we would name this as dinitrogen trioxide. So we have to put in the prefix di, change the ending to the "ide" ending, which is oxide in the case of oxygen. And now there's 3 atoms here, so we have to have the prefix tri. How about for this one? So this one, there's only a single carbon in the first element, so we don't need the prefix for this one. There's also a single atom of our oxide, so we change the ending to oxide. But in this case, we do need to represent the prefix with the ending element. So we need monoxide on the ending here. So we've got carbon monoxide. How about PCl5? So we know this is phosphorus. So that's going to be our first name. There's only one, so we don't need to use mono in this case. Just phosphorus will suffice. Now we need to change chlorine to the "ide" ending. So we've got chloride. And what is our prefix for 5? Hopefully you said penta. So now we need pentachloride. So this would be phosphorus pentachloride. So I actually think the naming of the covalent molecules is actually easier than the naming of our ionic molecules, because it all deals with the number of atoms that are involved in the bond. So now we've got disulfur tetraoxide. It's that easy for naming our covalent molecules. Hydrogen is an exception to the rule. It's always kind of this exception. Because it can only form one bond with anything else, it's really easy to name those compounds. So if we have H2S, we actually don't need to indicate how many hydrogens are going to be present. It's going to be obvious when it's formed. So we don't call this dihydrogen monosulfide. We can just call it hydrogen sulfide. We can skip the prefixes in the case of hydrogen. So it's easy because it's just hydrogen plus the anion in the hydrogen naming. You just skip the prefixes when you have hydrogen present. So practice our hydrogen exception. So we would call this hydrogen chloride. It's also known as hydrochloric acid because this is an acidic proton as well. How about this one? Hydrogen phosphide. How about water? It's hydrogen oxide, or more commonly, water. So let's get a little bit more practice naming our compounds. How would you name this one? Hopefully you said boron tribromide. How about this one? There's 2 of the nitrogens, so this would be dinitrogen. 5 oxygens, pentaoxide. How about this one? Ooh, that's a common name. What's the common name for this one? Yes, that's ammonia. How about this one? Hydrogen exception rule here. So we've got hydrogen and the anion, hydrogen fluoride. So it's not hydrogen monofluoride. So remember our hydrogen exception rule. How about if we write the names of these? Can we write our compounds? What would the molecular formula be for sulfur hexafluoride? Well, we know we have 1 sulfur and we have 6 fluorides, so it should be SF6. How about this one? Hydrogen sulfate. Ooh, sulfate is one of our polyatomic ions that we learned before. So if we look at our chart, we know the sulfate is SO4 with 1 hydrogen. So we know our sulfate is SO4, and we know the charge on that is 2 minus. So we're going to have to combine 2 hydrogens with that sulfate to make H2SO4. So our hydrogen exception, we may need to calculate the charge state to determine how many hydrogens are present, because we never have any prefixes with our hydrogen. So remember, you will have the polyatomic ion chart, and you will be able to utilize this to make our compounds. Hydrogen sulfate, even though this would be considered a covalent bond, hydrogen's actually acting as the cation in this case, and so it has ionic character when it starts behaving as an acid. So remember, we said recognize your acids by seeing hydrogen in the front position placed as the cation position in the molecule. How about diphosphorus tetroxide? But because the electronegativity difference is still below 1.7, these guys get classified as being covalent molecules, even though they have ionic character when they're dissolved. So again, hydrogen is that fickle one that can have properties of both covalent and ionic nature. So for the naming, we tend to name kind of in this combination of ionic covalent nomenclature, and that's why hydrogen is an exception to our covalent naming system. It's because it has characters that give it ionic character as well. Okay, so how about diphosphorus tetroxide? 2 phosphorus, so P2, tetraoxide, so tetra is 4, O4, so it should be P2O4. So our naming for all of the covalent compounds is pretty straightforward and easy. You just have to remember your hydrogen exception rule. Overall then, keys to successful nomenclature. First, you need to figure out, is it ionic or covalent? Metal plus nonmetal, typically ionic. Go with the ionic nomenclature that you learned from chapter 3. Nonmetals plus nonmetals, or hydrogen plus the nonmetal, are termed covalent. And so these will get the covalent nomenclatures. And we notice that hydrogen has an exception to the covalent nomenclature rules. So for our ionics, this is just a reminder from chapter 3. Name your cation, followed by the name of the anion altered to the ide form. Watch out for your transition metals. If they have more than one cation form, you have to indicate the charge on the cation using the Roman numeral. So like iron can take the +2 or +3 state. So remember, you need to indicate that you have iron 2 chloride versus iron 3 chloride, for an example. Also check for the presence of your polyatomic ions. These are mostly the anions, and you will have your table, so use it for help. This will be given to you on the exams as well. So our iron is a good example of our ionic compound. So we said iron 2 chloride versus iron 3 chloride. Since we have the transition metal, we need to indicate the iron state. So we've got iron 2 or iron 3, and this is indicating the charge state of the iron, not how many atoms are present. So our chlorine is the anion in this case, and so its name is coming last, and it'll be modified to the ide form. So it's chloride in both cases, but we tell them apart based on the charge state of the iron. So we have iron 2 chloride or iron 3 chloride as the IUPAC naming system. The old naming system would call it ferrous or ferric chloride. So for covalent compounds, we need to use the prefix system to tell how many atoms are present of each of the nonmetals. And this is because our nonmetals can often have multiple bond capabilities due to those unfilled d orbitals and the electron expansion rules that we have. We saw sulfur and phosphorus as good examples of these expanded d orbitals. So within our covalent compounds, the most electronegative partner is listed last, and it will be altered to the "-ide" form in the nomenclature. And then we have hydrogen exceptions to these rules. So when we have our example of carbon, when it combines with oxygen, we can have it combined with a single oxygen. In this case, it would be carbon monoxide. Remember, we drop the prefix if it's only one on the first element. And if it's combined with two oxygens, then we would name this as carbon dioxide. So in this case, our prefixes are going to indicate how many atoms we have present within our molecular formulas. So these are just given some of the structures and names of several binary molecular compounds that are shown. So we've got dinitrogen pentoxide and how it actually gets put together in its Lewis structure, in its structural diagrams. Boron tribromide, sulfur trioxide, and sulfur hexafluoride. So this table is very nice. It's just giving you a comparison then of different characteristics of both our molecular and our ionic compounds. So remember, we're saying our molecular compounds are those that are involved in covalent bonding. With ionic compounds, our smallest components are going to be the ions. These guys can actually dissociate and float around separately within a solution. In our molecular compounds, the smallest components are molecules. You do not get breakdown of the different elemental components in solution when they're sharing electrons. They have to stay close enough to keep sharing those electrons. So our smallest unit is the molecule inside the molecular compounds rather than the ions. The ionic compounds are usually composed of metals combined with nonmetals. Our molecular compounds are usually nonmetals with other nonmetals. Ionic compounds typically have very high melting points and very high boiling points because of the ionic nature. They're very, very strongly attracted to each other, and that means that they're very stable compounds and they don't like to change phases. So they'll typically be in the form of a solid at room temperature. They'll have very high melting points. Sodium chloride, for example, has a melting point of 801 degrees. Compare that to water's melting point at 0 degrees Celsius. So our molecular compounds have much less interactive force between the molecules because they don't carry full charges. So they're going to be typically gases, liquids, or low melting solids at room temperature. They have much lower melting points than our ionic compounds and much lower boiling points as well. So the boiling point for sodium chloride is up at 1413 degrees Celsius. That's a huge boiling point. You have to get this compound very, very hot before it goes into the gaseous state from the liquid. Versus water, whose boiling point's at 100 degrees Celsius, and longer hydrocarbon compounds that even have lower boiling points. Remember, our ionic compounds will conduct electricity when they're in their liquid state, so when they're molten, or when they're dissolved in water, and so they're broken apart into their ionic state. Nonmetals, on the other hand, and so therefore most covalent compounds or molecular compounds do not conduct electricity. They don't have the charge state required to be able to do that. Ionic compounds, there's many that are soluble in water because they contain these charged states. Comparatively, our molecular compounds typically have much more nonpolar consistency to them, and relatively few in comparison are going to be soluble in water. So ionic compounds then are typically not soluble in organic liquids that are nonpolar in nature. However, our molecular compounds have much more nonpolar component to them and typically will be soluble in nonpolar solvents or organic liquids.